So, good morning to everyone. Welcome to this interesting talk about model size reduction techniques. Uh, my name is Andrés Vélez Echeverri. I'm a staff ML engineer at Factor. Thank you to assist to this talk. So, I'm going to present the content we are going to review today. First, we are going to go through a motivation, why it is important to use model size reduction techniques. Um, then we are going to review use the principal two branches of model size reduction techniques. Afterwards, we are going to go deep into what is model distillation, how to apply model distillation, and when to do it. And at the end, we are going to review a demo in which we are going to program pretty much the loss function and also go through the model program in PyTorch Lightning. So uh, nowadays, it's pretty common to just hear this: the bigger, the better. That is because since 2018, we have seen different launch of models, for example, Elmo in this case, which take advantage of using unlabeled information, right, and use an structure of unsupervised learning in order to train different models. So when you use this setup, this schema, what you need is, in order to just extract patterns from your information from data, you need bigger models. So since 2018, with the launch of Elmo with 94 million parameters, we have seen an exponential trend in this behavior. So GPT, when it was launched, it had 110 million parameters, and then the first version, or BERT, has 340 million parameters. With each version of BERT or GPT, the models has increased in size. GPT-2 has 1.5 billion parameters, which is in the magnitude of billion right now. And with GPT-3, it has 175 billion parameters, which is a lot. We have also seen models in terms of trillion of parameters, which make complex to handle in edge devices. If we take a look into detail, the first version of BERT was distilled in distilled BERT, and the end product was a model with 66 million parameters. So this is like some advancements from NLP, but use computer vision doesn't fall behind. Computer vision nowadays has take advantage of unsupervised information in order to just leverage the potential of classification models. If we take a look into the SimClear V2, the methodology to train models using unsupervised like techniques, the authors introduce in their pipeline a model distillation component. So once the model is trained in an unsupervised way, they propose to you apply model distillation to deploy the model, or actually to use the model in a compressed way. This brings us to a question, and is basically, additionally, we have also some advancements this year with respect to this model we was launched, named Palm, with 540 billion parameters, and also the famous DALI V2 with 3.5 billion parameters. This brings us to a question of how to actually deploy these models, or how to use these models on edge devices. Nowadays, it's pretty common to actually use transfer learning on the models we just reviewed previously. But the question is how we actually use those models on edge devices. And actually, here we have a couple of constraints memory constraints, computational constraints. So actually, this still remain a challenge to actually ship those big models to edge devices. So when we have these kind of problems, it's really interesting to have some knowledge of the model size reduction techniques. They there are two main branches for this. The first branch is model quantization, right? Model quantization comes in different flavors. You could find model quantization in dynamic way, static, or aware training. There are multiple combinations between techniques of quantization, of how to quantize a model. The foundations of model quantization relies on map from float to integer types. So usually models are trained on float 32, float 16, and the objective is to map those types into integer forms. It's pretty common to just notice use of integer a, integer 6, or integer 4 when doing quantization. The other technique, the other branch, is to compress the model. For this, we have pruning and distillation. Those two techniques of this branch has a foundation basically to extract off components or parts or layers from the bigger model, from a big model, and just use as the result of this process and a smaller model with fewer parameters and faster in terms of computation. So we are going to review in a little bit of more detail model distillation. We are going to review the definition, what is important, how to apply it, and when to apply it. Okay, so what is model distillation? As I mentioned before, model distillation is part of model compression techniques. And in this case, we take a smaller model, which is named the student model, and then we train it to reproduce the behavior of a cumbersome model or a complex model, the teacher in this case. If we take a look into this image, we notice two loss functions, right? One function is computed with the soft labels output from the teacher model in combination with the soft predictions of the output of the student model. For this loss function, we use mean square error, and the objective is to close as much as possible the distances between those logics. The other loss function takes into account the hard predictions output by the student model, and also the hard labels or the ground truth information. So for this loss function, we actually use a cross entropy function. Okay, the question now is, how do we actually mix together those two loss functions in order to just create a single loss function? And here is the answer. Basically, we use a term which is named alpha, right? Beta is 1 minus alpha. So we multiply beta times the output of the MS error times alpha plus alpha times the cross entropy function. We are going to check more into detail how to code this loss function in the demo part. But right now, it's additionally important to just notice when to apply model distillation. So we need to take into consideration two aspects. when applying model distillation. The first one is you need to take a look into the device in which you are going to ship your model. You need to notice if you are going to use a GPU, right? Because after doing model distillation, the weight matrices is still in float types. So if you have a GPU, you could take advantage of this. In other cases, you could have SOCs with different configurations, such as NPUs or DSPs, which are SOCs optimized to work with quantization process. So in this scenario, you could apply distillation, but it's really important to, after distillation, quantize your model in order to take advantage of the SOC components. Another really important aspect when just deciding to use distillation is the training process. So the first point is you need to be allowed to retrain your model. So you need a configuration of teacher and a student way. You need to define what is the teacher, what is going to be the teacher, and also the student. Additionally to this, you will need a machine learning team in order to just handle the teacher and the student models, propose different combinations, and also to code the module which is in charge of doing the train and validation steps. And on top of that, I think one of the most important points is you need resources. So depending on the model you want to distill, you will need certain computation power. So I hope this is helpful. Then we are going to dive into a demo. So for this demo, we are going to review the dataset we use. We are going to just understand a little bit more in detail what kind of models we use for this demo. We are going to compute the loss function, train a model, and analyze the results, right? Just the training setup, which is called. So for the data, we are going to use the Hymenoptera dataset, which is a dataset in which the objective is to classify if an image has a bee or ants, right? And is a toy dataset is for illustration purposes, right? For the training part, we have 124 image of ants and 121 image of bees. So we are going to review what configuration of models we are going to use. So for the teacher model, right, we are using a ResNet 50. ResNet 50 has 23 million approximately. And for the student model, we are going to use a ResNet 18, which has around 8 million parameters. The teacher model was trained on ImageNet, right? And then I fine-tuned for 25 epochs with a batch size of 32, and this magnitude or learning rate, momentum, and a linear scheduler. The student basically was taken from Torch Vision's models, and we are going to review right now. So when distilling a model, it's really important to just take into account these principal points. Is the model selection, the teacher and the student, the loss function. This model using the dataset of bees and ants, right? I have this model located in this machine, actually in this folder, which is called models, right? So we are going to load this model. So Torch load the path of the model. And additionally to this, I'm using a map location since I use a GPU to fine-tune my model. But in this setup right now, I have a CPU and I don't count on a GPU. So we have our teacher model, and then we are going to just load our student model. So as I mentioned before, we are using the weights of the trained model on ImageNet. We use the torch vision models ResNet 18 with the weights after train on ImageNet. And this is our student model. Additionally to this, we need to do some extra configurations, which is we are not going to train our teacher model. So what we are doing right now is to freeze all the parameters of the teacher model, and then we are here freezing some parameters of the student model. Right? We are only going to train the linear layer of the student model, which is this we are defining here. So touch linear function equal to output of dimension of 2. Also, we want to make sure and know what is the amount of parameters each model has for the training process and no training process. So we take a look into this function I defined. So we are going through for each parameter of the model. We are checking if the model requires graph, right? And then we are summing all this together. We are using this variable trainable total params in order to store the number of total parameters to train, and the same happens for the not trainable parameters. At the end, what we are printing here is the information for the teacher model. We actually not training the teacher model. There are no trainable parameters. And for the student model, we are freezing pretty much all the parameters, and we are leaving just the linear layer to fine tune it. Okay, so the next step when doing model distillation is to define the loss function, right? As we went previously through the theoretical explanation, we use a combination of the mean square error and the cross entropy in a combination. So this is the mathematical formation back again, but how this formula will look into code, we are going to check. For this, we are going to define a distillation loss function, and is going to have as inputs the teacher predictions, the student predictions, the ground truth labels, and also an alpha value. We define the losses using torch, NL, MS loss, and also for the cross entropy. To compute the mean square error loss, we are going to use the teacher predictions as well as the student predictions. Since I mentioned this before, it's important to closen the distances between those two components, since we want to be like our teacher. For the cross entropy loss, we have our student predictions, and we use also the ground truth labels. This cross entropy and the mean square error function, loss function, is mixed together in this way. So beta is equal to 1 minus alpha, right, times the mean square error loss function, plus alpha times the cross entropy loss function. So this is a way to make sure those two loss functions in just one function. Additionally to this, it is really important to configure accordingly the module. In this case, we are using a PyTorch Lightning extension module to define the general train and validation steps. As we see in our constructor, we are defining the teacher, student, alpha, and the loss function. The loss function is as the one we defined previously, right? Is as default, set as default. For the teacher, student, alpha values, and the loss function, are past the models we loaded before. We are also instantiating some metrics from torch metrics and creating a dictionary with those components in order to facilitate when doing the train and validation step. An additional really important step is to configure accordingly your optimizer. In this case, you want to use just the parameters of the student model in order to configure your optimizer. We are using in this case an Adam optimizer with a learning rate of this magnitude. In the forward function, which is a helper function, we are taking a mode as input and also a batch. The mode helps us to decide if we are in train or validation mode, and then we decompress the batch into the information, the input, and the ground truth labels. We pass the input information for both the student and the teacher model, computing the logics for both of those models. These logics, we are going to use them to compute the accuracy, as we see here, the predict of the student with the ground truth, and also we are going to compute the distance between the teacher and the student logics. We also use the absolute value of this calculation, and we average it together by the batch. We input the predictions of the teacher and the student, and also the ground truth labels and the alpha value to the loss function we defined previously. And at the end, we just log into the TensorBoard logging callback or information. Here in the training and the step function, we notice how we use the forward function defined previously in order to just do the needed computations. So these are the principal components when defining a module and applying model distillation. To exemplify model distillation and running some experiments and also checking the importance of calibrating alpha, I ran different experiments with values of alpha taking 0, 0.5, and 1.2. Each value of alpha was run 4 times with the same training configurations used during training, the teacher's fine-tuning process. In our case, the student model was previously trained on ImageNet, as I mentioned before. We took those weights as the initial starting point. However, it is recommended to initialize the student model with the weights of the teacher model. What you do is to extract slices of the layers of the teacher model in order to create a smaller version of this model. This is recommended because by doing this, you are, or what is presented is you stabilize your training process, the loss function, and also the accuracy. We are going to look into detail right now at the results. We are going to analyze the results in different components. We are going to check the loss function results when modifying or taking different alpha values, as well as the accuracy and the similarity between teacher and the student logics predictions. So let's begin with the loss function. When using alpha equal to 1, so just the cross entropy, we notice the loss function is more stable than when we use an alpha equivalent to 0, which in this case is just using the mean square error. In this case, It takes a little bit, so approximately 7 epochs to converge to a value. If we look into detail when using a mixture of these values, an intermediate value of alpha equal to zero point 0.5, we just notice we have a combination of those two processes. So it's more equilibrated process. Let's analyze the accuracy. When using alpha equal to 1, so use cross entropy, the accuracy values begin increasing from as low as 7, 0.7. Eventually, it converges to 0.94. So this value alpha has a higher risk of convergence than when using the others two possible combinations values. So since we have seen the loss function decreases in a stable manner and is preferred to use alpha equal to 0.5. For the teacher and the student logics, we have the following. So the difference between the teacher and the student logics when using alpha equal to 0 and 0.5 evolves in a similar manner. This means the optimization process is behaving as expected, since what we want is to those logics to be as close as possible, as equal as possible. On the contrary, when we use an alpha equivalent to 1, the illustration shows us that there is no involuntary process to mimic the teacher logics. They are two different away. Also, it can be inferred from this that the parameter distribution explores other regions, bringing different local parameter meaning. As some conclusion, when using an alpha value of 0.5, we have a more stable loss function. The accuracy converges in a stable manner, and the logics tend to generalize accordingly to the teacher model. By taking use the cross entropy and the mean square error, the process suffers in occasion of loss function or the logics, mimicking the logics. So as a conclusion, to wrap up, is when the models are small, they struggle to generalize. This problem can be solved using the teacher model logics by introducing a component of mean square error in the loss function. So you take advantage of not using just the labeled information, but also a bigger model or like a guide to just take advantage and maximize this knowledge as possible. So model distillation is a really interesting aspect of how to compress your models in a simple manner. It's a really interesting topic to be used nowadays, and also with a huge impact when using models on edge devices. So thank you for attending to this talk, and I enjoyed this process of distillation of your models. Thank you.